Hello everyone, I welcome you all to Startup Academy. This academy is exclusively for ISS only. In the previous lecture, we started with the last topic of our chapter, demand analysis, in which we did utility function. In today's lecture, we'll move forward in utility function. In yesterday's topic, we did what is utility function and how do we find out a utility function when a rate of change of utility function with respect to x1 and x2 and x size in general. We did that and one question on that so that we can understand it on a deeper level. In today's lecture, we'll move forward with the utility function. The topic for today's lecture is uh, constrained utility maximization. Now, what do we mean by constrained utility maximization? Suppose I am using two utilities. Suppose I am using, yesterday I was using wheat, today I'm using wheat and rice, two utilities, wheat and rice. And I want to maximize the utility, means I want to maximize my satisfaction level on spending on rice and wheat respectively. So that is constrained utility maximization. Constraint means when we are constrained means when we are bound on number of commodities. Number of commodities can be infinite, but we are bound here. We have to take the n number of commodities which are countable, not infinite, and the quantity is also finite, so that we can compare it in mathematical terms. That's where the topic constrained utility maximization is coming from. So let us consider we have two commodities, x1 and x2. These are two commodities, and we have to find the maximum satisfaction level of these two commodities that is used by an individual. Suppose an individual I is using these two commodities, x1 and x2, and we have to find its utility function. So the utility function will be a function of these both x1 and x2 respectively, right? So let us denote that if we have y naught, then y naught is the total income or total amount spent on this x1 and x2. X1 and x2. Let P1 be the total amount spent on x1 and P2 be the total amount spent on x2. On commodity x1 and x2. Okay, so now we can frame the utility function as y naught equals to the quantity of x1 into the price of x1 plus the quantity of x2 into the price of x2. This is the utility function of our x1 and x2. Now if we want to find the utility function, then we have to convert this utility function in a function of one variable. Here the utility function is the function of two variables, so we have to convert it firstly into one variable. So let us take, suppose we are taking it equals to x2. Suppose we are taking the values of x2 as y naught minus x1 p1 upon p2. This is our x2. So we can say that utility function is the function of x1, and instead of x2 we can write y naught minus x1 p1 upon P2. These are the utility function of this. It becomes a utility function which can be referred to as the function of x1, and here we are denoting function as phi instead of f. So this can be written as a function of f1. Now we have to maximize this function, this utility function phi x1, so as to we have to maximize this so that our x1 and x2 we'll get from it. So, how to maximize this? We will differentiate this utility function with respect to x1, first of all. And if we double differentiate this utility function with respect to x1, then it should be less than 0. Here we will put equal to 0 and we'll get the value of x1 equals to something. Suppose x1 is 4, then we'll put 4 this value 4 in our equation of x2, and we get the value of x2 as well, and this should be less than 0. This is an important property because we are doing maximization, and with differentiation a maximization can be achieved when the double differentiation of a function is less than 0. Okay, so this is what we had to do. We had to do about constrained utility function or maximization. Now there are two conditions. First is necessary condition and the other one is sufficient condition. If I say about necessary condition, necessary condition in necessary condition, we know that we have to differentiate this with respect to, suppose we have taken the utility function. Utility function equals to differentiate of f with respect to x1 plus differentiate of f with respect to x2, and we also have dx1 and dx2 here. dx1 differentiate of f with respect to x2 dx2. If we differentiate this whole equation of utility function, then this we know that if we divide all of this equation by dx1, so we will be getting du upon dx1 equals to delta f upon delta x1 plus delta f upon delta x2 into dx2 upon dx1. Now this dx2 upon dx1, we have considered an equation, this one, this equation x2. If we differentiate this x2 with respect to x1, we will be getting minus p1 upon p2 according to the according to the rules of differentiation. We will be getting minus p1 upon p2. If we keep that value here, we will be getting delta u upon dx1 equals to delta f upon delta x1 minus p1 upon p2 delta f upon delta x2. We'll get this. Now if we put this value, because we had to keep this value equals to 0 to get x1, here we discussed about this. So if we put this equals to 0, then we'll be getting delta f upon delta x1 equals to p1 upon p2 delta f upon delta x2. Now this delta f upon delta x1, I am writing it as delta f as f x1 equals to p1 upon p2 f x2. If I equalize this, fx1 upon x1 equals to fx2 upon x2. This becomes one more equation, which forms our necessary condition, which states that the marginal utility function fx1 is nothing but marginal utility function of x1 with respect to x1 should be equal to marginal utility function of x2 with respect to x2. This is our necessary condition for maximization of a utility function. Okay. Now comes the second condition, which is sufficient condition. The first one is only necessary condition, it is not sufficient. But the second one is sufficient. Sufficient conditions says that the double differentiation of the utility function, or here we have taken, instead of the utility function we have taken phi x, the double differentiation of phi x1 with respect to x1 square should be less than 0. Or if we are taking it in terms of x2, then we can say that the double differentiation of phi x2 with respect to x2 should be less than 0. This forms the sufficient condition of our equation. Okay. So this here the topic is over. We'll do one example so that we'll understand it more clearly. We have been given a utility function which is uh, 4x1 x2 minus 4x1 x2 minus x square with respect to the constraint of prices given as 20x1 plus 10x2 is equals to 60. The total amount has been given as 60, and the amount of the commodity x1 is 20 and the amount of the commodity x2 is 10. So these two equations have been given, and we have to determine the optimum level of commodities to maximize this utility and spend his total money. Means we have to find the prices or the amount of x1 and x2, or the quantities of x1 and x2, or the or we have to find simply x1 and x2 so that this utility function gets maximizes. Okay. So the first step would be, we will take this as a function of only one variable. Here utility function is the function of two variables x1 and x2. Here we can take it as a function of x1 or x2, one of them. We can write this equation as this. Taking 10 common from each side and cancelling them, we can write this as equation this. So x2 can be written as 6 minus 2x1, or instead, if we take 2 common, 3 minus x1. x2 is given as this. Now keeping this in the utility function, 4x1, x1 remain as it is. Instead of x2, we write it as 2 into 2, 3 minus x1 minus x2 whole square. x2 whole square means 2 into 3 minus x1 whole square. If we solve this, we will be getting 8 3s are 24 x1 minus 4 2s are 8 8 x1 square, and here we will be getting minus 4 9 plus x1 square minus 6 x1. On solving it further, 24x1 minus 8x1 square minus 36 minus 4x1 square plus 4 6 are 24x1. So on solving this, we get our utility function as the function of only x1 which is given by minus 20 minus 12x1 square plus 48x1 minus 8 minus 36. Okay, this is our utility function. Now what we'll do, we'll differentiate this utility function with respect to x1. If we differentiate this with respect to x1, we will getting minus 24x1 plus 48, right? And the first condition was to keep it equal to 0 so as to get the value of x1. If we keep this equal to 0, we will be getting 24x1 equals to 48, and hence x1 should be equal to 2. We got x1 equals to 2. And keeping this x1 in this equation, x2 equals to 6 minus 2 into x1, which is 2. So we get our x2 as 2. But we have got this, but we have to check whether our utility function is maximizing or not. For that, we have to double differentiate this utility function with respect to x1. So we have to differentiate it one more time, which is minus 24x1 plus 48. If we differentiate it one more time with respect to x1, we will getting minus 24, which is obviously less than 0. So hence we can say that the utility function maximizes here with the prices or amount of x1 as 2 and x2 as 2. X1 and x2 both are coming equal by chance here. So that's the case. So we can say that the consumer should purchase x1 equals to 2 units of commodity of x1 units of commodity x1 and units of commodity x2 in order to make this purchase of maximum utilization or maximum satisfaction or maximum utility function, whatever you can say. You can write that in the answer. So this completes our demand analysis, and there is one general form also given, but that's not in your syllabus. Only till here demand analysis is in your syllabus. I hope that you got whatever we have done today in the class, and this also completes with demand analysis. This also completes our statistics paper 3, which is of subjective type. I hope that all the topics are clear with all of you, and if not, then you can ask in the comment section or on our WhatsApp channel. All the best. Thank you.